This is the first part of a series of videos that will focus on temperature sensors. In this video, we will discuss temperature and go over desirable temperature sensor characteristics. So, why should you learn about temperature sensors? Well, you may be interested in measuring water temperature with your underwater robot. A knowledge of temperature sensor characteristics will be really useful in selecting the appropriate sensor for this application. As practicing engineers, you may be involved in a project that requires temperature sensing. If you choose to work in the automotive industry, the engine temperature, the temperature inside the cabin, and the ambient temperature all need to be known by the driver. In homes, temperature sensors inside an oven are essential to baking the perfect dish. And thermostats ensure that temperatures inside the home are just right. Temperature sensors are also important in hospitals. An application that is particularly important is the monitoring of body temperatures of babies who are born prematurely. Their lives depend on temperature sensors. So, we will be discussing sensors that measure temperature. But what exactly is temperature? We typically learn at a young age not to touch hot objects because doing so really hurts. Furthermore, many of us have been told to bundle up when going outside when temperatures are low, or we risk catching a cold. Therefore, we learn early on that energy is transferred from something that is at a higher temperature into something that is at a lower temperature when the two are in contact with each other. And that is actually a correct and overly simplified description of temperature. Let's take a look at this video, which shows particles in a box that are separated by a barrier. On the left side of the barrier, there are blue particles that are moving around a lot slower than the more energetic red particles on the right side of the barrier. The blue particles are less energetic relative to the red particles and are therefore defined as cold. The red particles are more energetic and are therefore defined as hot. What happens if this barrier instantly disappears? Once the barrier disappears, the blue particles come into direct contact with the red particles. Energy is transferred from the more energetic red particles to the less energetic blue particles, and all the particles in the box become pink, which indicates that they have achieved a new state of equilibrium and have an energy that is between that of the blue particles and the red particles. This video demonstrates a widely used, simplified definition of temperature, which is temperature is a measure of the tendency of an object to spontaneously give up energy to its surroundings. When two objects are in thermal contact, the one that tends to spontaneously lose energy is at the higher temperature. When the barrier between the particles disappeared, the high temperature particles made contact with the lower temperature blue particles, causing a transfer of energy. Eventually, all the particles in the box reached a thermal equilibrium. Now, as this slide shows, this is an overly simplified description of temperature. Particles just don't bounce around and hit each other. The activities of particles also includes vibration, rotation, and collective behavior. However, a more detailed description of temperature is beyond the scope of these introductory videos, and you will learn all about temperature and the laws of thermodynamics in E82. For now, it is sufficient to know the description of temperature shown here. This series of videos is focused on measuring temperature. There are times when we know that something is clearly at a much higher temperature than room temperature. For example, if we're curious about how hot lava is, we can stick a temperature sensor into lava. In this course, you may be interested in ocean temperatures and how they change with depth. Ocean temperatures are not clear just by looking at the ocean, and when you stick a temperature sensor just beneath the surface of the water, this will not give you the temperature at a depth of 900 meters. So, how is the change of ocean temperature with depth measured and monitored? Well, a team at the National Oceanic and Atmospheric Administration is using autonomous underwater gliders to do this.
Hello, we're here today to talk about the new underwater glider project that we have at NOAA AOML. This project is carried out together with the University of Miami, with the University of Puerto Rico Mayagüez, and the Maritime Authority of the Dominican Republic, together with the CARICUS Regional Association. The objective of this work is to carry out ocean observations with the underwater gliders to measure temperature and salinity, with the objective of improving the seasonal forecast of tropical cyclones and the intensification forecast of hurricanes in the Caribbean Sea and tropical North Atlantic.
The first aspect of AOML's underwater glider project involves going out to the study area and actually collecting data with the gliders. Once a glider is deployed from a surface ship, it uses small changes in buoyancy and its wings to achieve forward motion. Directional changes are achieved using the glider's internal adjustable ballast, rolling to the left or the right depending on the location of the next waypoint. Using these methods versus using a motor-driven propeller and movable wings allows the glider to operate for a much longer period of time than a standard AUV. These gliders can operate for up to 10 months continuously, traveling over 3,000 miles at a speed of roughly 1/2 a mile per hour. The glider navigates using a combination of GPS while at the surface and its internal sensors that monitor vehicle heading, depth, and angle during a dive.
These gliders were developed to accommodate a wide range of sensors, allowing for the measurement of temperature, salinity, pressure, dissolved oxygen, dissolved carbon dioxide, and pH. During its time on the surface, the glider will update its position via satellite and transmit scientific data. The glider can also receive commands from the pilots on land for improving flight efficiency as well as the quality of the collected data.
The gliders are autonomous, but they are controlled remotely via satellite by the pilot sitting at the NOAA lab. The pilot is constantly monitoring all the movement of the vehicle, as well as the data that is being recorded, and is also sending commands to the glider to control how the glider dives, navigates, and collects data.
The second aspect of this project is the analysis of data from these observations. The data obtained from these deployments will be analyzed alongside other in situ observations from a variety of platforms.
In this video, you see that an autonomous underwater glider is used to measure temperatures at depths as low as 860 meters. The autonomous glider measures temperature as it dives down, and as it hits a desired depth, it measures temperature as it glides back upwards. A graph of temperature versus depth from one of the runs is shown on the right. Here we see that the temperature is about 30 degrees just below the surface of the water, but it drops all the way down to about 6 degrees at a depth of about 875 meters. The descending profile and the ascending profiles are shown, and they closely match. Glider AUVs don't require a lot of energy to operate, and ocean temperatures can be measured continuously for several days. This is really cool stuff. So, if you're interested in measuring temperature, you need to ask yourself several important questions about the characteristics of the temperature sensor that will enable you to achieve your goals. You need to consider the accuracy of your temperature sensor. How accurate do you need it to be? Is it okay for your sensor to be off by 1 degree Celsius? Or do you need your measurements to be accurate to within 1/10 of a degree Celsius? Your temperature sensor will output a signal, such as a resistance or a voltage. Do you need a less accurate sensor with a simple relationship between sensor output and temperature? Or are you okay with a more accurate sensor that requires a table or equation to convert output into temperature? It would be desirable to have a sensor that has repeatable measurements. If you repeatedly dip a temperature sensor into a glass of water at room temperature, it should give you the same reading over and over again. Response time is another important characteristic of temperature sensors. Will your robot be descending rapidly or slowly? Will a sensor response time of 4 to 60 seconds be sufficient? Or will you be needing a sensor with a response time of less than a second? These are important questions to ask because if a slow sensor is placed into an AUV that descends rapidly, the sensor may not be able to track the rate of temperature change. A critical property of a temperature measurement device is how quickly it responds to a change in external temperature. Let's do a quick review of a thermal system step response. Imagine that you have a temperature sensor that is immersed in an ice bath, which is at 0 degrees Celsius. You then take the temperature sensor and instantaneously move it into a beaker of boiling water, which is at 100 degrees Celsius. Therefore, your sensor experiences a step input that goes from 0 degrees Celsius to 100 degrees Celsius at a time of 0 seconds. If you are monitoring the output of your temperature sensor, you will see that it takes some time to reach the temperature of the new environment. The thermal time constant, tau, is the time it takes to get to 1 over E of the final temperature, or 63% of the final temperature, which in this case is 63 degrees Celsius. The smaller your time constant tau, the faster the response time of your temperature sensor. What about temperature range? Is a range of negative 55 degrees Celsius to positive 150 degrees Celsius sufficient for your application? Or do you expect temperatures to range between negative 100 degrees Celsius to positive 450 degrees Celsius? Calibration is another important characteristic for a temperature sensor. A temperature sensor that is easy to calibrate is desirable, but easy calibration could come with trade-offs and other characteristics, such as accuracy and temperature range. The cost of your temperature sensor will also be important. You will have a budget for your project, and you may not want to spend a majority of that budget on a single temperature sensor. However, temperature sensors with lower costs could be less accurate or may have a slow response. A key point in this discussion of temperature sensor characteristics is that you should plan out your experiments before you even start them. You should be conducting extensive research on the phenomenon that you want to measure, and use the information from your research when you make a decision on which temperature sensor to use. Here is a table that we will be revisiting throughout this series of videos. This table will enable the side-by-side comparison of the characteristics of common temperature sensors that you could use in the lab. In summary, temperature is a measure of the tendency of an object to spontaneously give up energy to its surroundings. When two objects are in thermal contact, the one that tends to spontaneously lose energy is at the higher temperature. Desirable temperature characteristics include accuracy, a simple relationship between sensor output and temperature, repeatability, fast response, wide temperature range, easy calibration, and low cost. Now let's take a quiz. We spent some time discussing the autonomous glider project in this video. Based on the results presented in this video, how does temperature change with depth in the Caribbean Sea? Please pause the video, give this question some thought, choose an answer, and unpause the video to see the correct answer. The correct answer is C. Based on the results shown here, temperature decreases with depth in the Caribbean Sea. Furthermore, the measurements are relatively consistent over a span of several days.